Hi everyone, welcome back to my channel. In this video, I am going to explain one of the important concepts from coordination chemistry, that is CFSE, that means Crystal Field Stabilization Energy. This is one of the important concept for CSIR NET and GATE exam. Now, let's move to the concept. First, we will see what is crystal field theory. When ligand approach a transition metal ion, the 5d orbitals no longer have the same energy. They are no longer degenerate. Instead, they split into two energy levels. See, for an octahedral complex, you will get two energy levels. One for higher energy, it will mention as a EG, dz square and dx square minus y square orbital. Here delta naught is mentioned as plus zero point 0.6, and for lower energy T2G, dxy dxz and dyz orbital may be mentioned as minus zero point 0.4 delta naught, where delta naught is equal to octahedral crystal field splitting energy. So this is the energy levels for an octahedral complex. Now we'll see why the splitting occurs. Ligands approach along x, y and z axes. Orbitals pointing directly towards ligand experience more repulsion. Hence Hence, dz square and dx square minus y square. These two orbitals they move to higher energy. These are called Eg. So the remaining three orbitals dxy, dxz and dyz that lie between axes, they experience less repulsion. These become T2G. Now we'll see energy values you must memorize for octahedral complex. For T2G orbital, energy is minus zero point 0.4 delta naught, and for EG orbital, energy is plus 0.6 delta naught. These two numbers are the most important in CFT, and please remember these values. This is important for solving the question. Now, we'll see the formula for CFSE. CFSE is equal to minus 0.4 NT plus 0.6 Ne into delta naught, where Nt is equal to electrons in T2G and Ne is equal to electrons in Eg. So, we'll see the example. We'll take as a D1 as an example. For D1, electronic configuration is T2G and Eg. For D1, electrons we will fill in T2G orbital. So, for T2G, energy is minus 0.4 delta naught. So, one electron present. So, CFSE is equal to 1 into minus 0.4 delta naught, that equal to minus 0.4 delta naught. Now we'll see the another example for D2 orbital. For D2 orbital, electronic configuration to EG and T2G, we have to fill electrons in T2G orbitals. The two electrons brothers. So CFSE is equal to 2 into minus 0.4, that equal to minus 0.5. Here CFSE is equal to minus 0.8 delta naught. Now we'll see the another example D3 orbital. For that, electronic configuration is Eg and T2G, and 3 electrons also filled in T2G orbital. So CFSE is equal to 3 into minus 0.4, that equal to minus 1.2 delta naught. Now we'll see high spin versus low spin concept. Electrons have two choices. One is pair in lower orbitals, and second one is occupy higher orbitals. The decision depends on crystal field splitting and pairing energy P. Now we'll see if delta naught less than P means pairing energy, electrons avoid pairing. This is a high spin complex. If delta naught greater than P, electrons pair first, that is low spin complex. Now we'll see the example, that is D4. For D4, we'll see the high spin example. If D4 is high spin, electrons filled between both orbital T2G and EG. First, that will fill to T2G orbital, then it will move to um, higher energy level. So, see here, we'll calculate CFSE. In T2G orbital, 3 electrons present. So, 3 into minus zero point 0.4 plus 1 into 0.6, that is equal to minus 0.6 delta naught. Now, we'll see for the same D4 orbital, we'll see low spin as an example. In low spin, first we have to pair, first we have to do pairing in lower energy orbital. So first, so orbitals will fill. You have to first fill the electrons in lower energy orbital. So here pairing will present. So now we will. So EG will remain as a empty. So we will calculate CFSE. 4 into minus zero point 0.4, that equal to minus 1.6 delta naught. Now notice that low spin complexes gain more stabilization from CFS through pairing energy must also be considered. So see here in T2G orbital pairing is presented, so it is more stable through CFSE. Now we'll see the CFSE table for octahedral. Actually this is very important for the exam, you must remember so that you can save time. We'll see dn orbital high spin and low spin. For d0 orbital high spin is 0 and low spin also 0. This is CFS value. And for d1 high spin is minus zero point 0.4 delta naught and low spin is minus zero point 0.4 delta naught. And for d2 high spin is minus zero point 0.8 delta naught and low spin also minus zero point 0.8 delta naught. And for d3 high spin is minus 1.2 delta naught and low spin also minus 1.2 delta naught. And for d4 high spin is minus zero point 0.6 delta naught and low spin also minus 1.6 delta naught. And for d5 high spin is 0 and low spin is minus 2 delta naught. Now for d6 high spin is minus zero point 0.4 delta naught and low spin is minus 2.4 delta naught. And for d7 high spin is minus zero point 0.8 delta naught and low spin is minus 1.8 delta naught. And for d8 high spin is minus 1.2 delta naught and low spin is minus 1.2 delta naught. And for d9 high spin is minus zero point 0.6 delta naught and low spin is minus zero point 0.6 delta naught. And for d10 both high spin and low spin value is 0. So please remember this table, it is very important for solving the question. Now we will see the pairing energy. Many CSIR NET questions ask for the total stabilization. So we'll calculate total. So we'll see the formula for total energy. Total energy is equal to CFSE plus M into P. Here M is the number of electron pairs formed in the d orbitals due to crystal field filling. Now we'll see the example. A low spin D6 configuration. Low spin D6 configuration means there are two orbital EG and T2G. First we have to fill lower energy orbital D6 we have to fill in T2G orbital first. So it will get 6 orbitals, 6 electrons also we will filled in T2G orbital. So electrons get paired. You got a 3 pairing electron here. So here CFS is equal to 6 into minus zero point 0.4, you will get a minus 2.4 delta naught. There are 3 paired electron sets in the T2G orbitals. So when comparing configurations, include the appropriate pairing energy term. Now, we'll see the tetrahedral complexes. In earlier slides, we have studied about octahedral complexes. Now, we will see the tetrahedral complexes. Here, splitting is reversed. Higher is T2, lower is E. In octahedral, higher is E orbital and lower is T2 orbital. So, now we'll see the concept. Here, the splitting is smaller. Delta T is equal to 4 by 9 delta naught. And plus, please remember this formula. Now we'll see energy values becomes. Here E is equal to minus 0.6 delta T and T2 is equal to plus 0.4 delta T. Since delta T is small, tetrahedral complexes are almost always have high spin. So now we will see spectrochemical series. Actually, this is very important for CSIR NET and GATE. In from coordination chemistry, most of the questions they will ask for from the spectrochemical series. So you must remember this spectrochemical series. We'll see here I have mentioned spectrochemical series from weak field to strong field. We'll see the ions here. I minus less than Br minus Cl minus F minus OH minus H2O NH3 En NO2 minus Cn minus and CO. Here halide part I minus 2OH minus. These are the weak field ligands and CO, Cn minus NO2 and En. This right hand side end is the strong field ligand and NH3 this is the neutral ligand or intermediate ligand. Now we'll see the weak field ligands I minus Br minus Cl minus F minus and O minus. These are the weak field ligands and also these having small delta naught. These usually form high spin complexes. Weak field ligands having small delta naught and also it forms high spin complexes. And next we'll see the intermediate field ligands also called as neutral ligands. H2O pyridine NH3 ethylene diamine EN. These are the intermediate field ligands. Now we'll see strong field ligands. Strong field ligands usually having large delta naught, NO2 minus, Cn minus and Cu. These often form low spin complexes for D4, D7 octahedral ions. So, strong field ligands always have large delta naught. Actually, this is most important. I hope you understood this concept. In next video, we will solve CSIR NET and GATE previous year questions from this concept. If you like this video, please like, share and subscribe to my channel. Thank you. Have a good day.